and today I'm going to be talking to you about using loop extrusion to model metaphase DNA. So the reason why we are doing this is that different cellular stages will respond to ionizing radiation differently. Now this has really large implications for treating cancer patients because a good understanding of how a certain type of cell will respond to ionizing radiation is really important in knowing how to kill it and not to overdose your patient. So in order to get a better understanding of this, our group here at UTA with Dr. Chi performs Monte Carlo simulations in order to better understand that. However, to run these simulations, we first need to have models of DNA which we can irradiate. However, that model does not readily exist for metaphase DNA, which motivates this study. So the model which we based our model on is known as the loop extrusion model. A little bit of tongue twister there. Here in the loop extrusion model, these large proteins, which in our simulation have a left and right side, bind onto the DNA. And when they bind on, they pull the DNA through itself, forming these loops over time, which progressively get larger and larger. Now, these loop extrusion factors are dynamic, meaning they're able to bind on and bind off, and they have a certain residency time, which they stay onto the DNA. But the number of loop extrusion factors in the simulation stays constant, because when one unbinds, it rebinds somewhere else randomly on the chain. So since these loop extrusion factors are so large, they could eventually extrude to the point where they come into contact with each other, and at that point, the extrusion stops at that time, at that site. But the sides of the loop extrusion factor, which aren't in contact with other LEFs, are able to continue extruding, which is a really important point of this model because it enables a very high density of loops to be achieved. These loop extrusion factors finally can also bind onto loops formed by other loop extrusion factors. So moving on to our methodology, despite advances in computational power, we still can't model this thing with base pair by base pair accuracy. Instead, what we have to do is we have to use a coarse-grained polymer model where each monomer represents a nucleosome which has 200 base pairs in it. In each simulation, we run 120,000 monomers, so that equates to 24 million base pairs per simulation. So the first part in running a simulation is that we have to simulate where the loop extrusion factors are, and that's done according to the ways of this diagram. It's run in a 1D simulation, and that assigns along a list of an index list of which monomer has a loop extrusion factor on it, and from there you'll see that there's some special forces which are applied to that. Next, we go to the initialization of the positions of the monomers themselves. So it first starts out as these little wedges which extrude outwards from like the central spiral. And from step 1 and 2, that's kind of these are simplified model versions. And in step 3, you can see that like the full density is made in our initialization model, which is really dense, and the areas between the loops is also filled because not every single DNA chain is a part of a loop. So that kind of fills up this central gap here in this model. So once these initial positions of the monomers are made and the loop extrusion factors have been simulated, we can finally apply the forces to our model using an open source library known as OpenMM. So this has a bond force which kind of keeps all the monomers connected to each other, a repulsive force which is similar to an electron Coulomb force, which repels everything apart. And then there's these forces between loop extrusion factors which keep them bound together, as well as they tether the loop extrusion factors to a central spiral. And then there's also a bending stiffness force which kind of prevents the DNA from freely flopping around and forming kinks. So our result is this 3D model of confined in a cylinder, and to test our results, we measure a contact map, which kind of just measures the density of the loop of the model at different regions, so we can kind of get an idea of how dense our model is compared to real-world measurements, which are shown in the green and orange line. So with this, we hope that we can perform Monte Carlo simulations more efficiently and effectively than we could before and get a better understanding of what happens. Thank you for listening, and I hope you have a good day.